You can also determine the order of a reactant graphically. If you graph the concentration of a reactant versus time and you get a straight line, that tells you that that reactant is zero order. It also tells you that the rate constant is equal to the negative slope. If you graph the natural log of the concentration of a reactant versus time and you get a straight line, that tells you that this reactant is first order and that the rate constant is equal to the negative slope. And finally, if you graph the inverse of the concentration of a reactant versus time, and you get a straight line, that tells you that this reactant is second order, and the rate constant is going to be equal to the slope. In this problem, it's found that the natural log of this reactant when plotted versus time gives a straight line. So that right there tells us that this is first order. And we can see here when it's first order that the rate constant is equal to the negative slope. So for the rate constant, we would make the slope positive and enter that number. And this one, a graph of this reactant with no modifications versus time gave a straight line. So we know that it's zero order. And the rate constant for the zero order is equal to the negative slope. So again, we just change the sign. This one, I've graphed 1 over the concentration of the reactant versus time, and it gives a straight line slope. So we know that this is second order. And on the second order, the rate constant is equal to the slope as it is. In order for any two compounds to react, they have to collide with one another. They also have to collide with each other with enough energy to make the reaction happen. This amount of energy is known as the activation energy. The activation energy is the amount of energy that the molecules must collide with in order to react. The amount of activation energy required depends on many variables, but two of the most important are the rate constant and the temperature. For the next few problems, we will use this equation. K1 stands for rate constant 1, K2 stands for rate constant 2, EA stands for the activation energy, which has to be in joules. T1 stands for temperature 1, T2 stands for temperature 2, and both of the temperatures have to be in Kelvin. And then this number, 8.31, is the gas constant, and it goes in for R. And we're going to start by making a list of our givens. Here we have the activation energy. 587 will be our temperature 1 in Kelvin like we want it to be, and then our rate constant 1 is going to be 1.08 times 10 to the negative third per second. The rate constant 2 will be 8.81 times 10 to the negative 3 per second, and it's wanting us to find temperature 2. So we're going to plug numbers in here. ln of K2, 8.81 times 10 to the negative 3 over K1, 1.08 times 10 to the negative 3 equals negative. Activation energy is here, but we need that activation energy to be in joules, so we move the decimal point to the right and we put in 173000 divided by R, which is 8.31, times 1 over T2, which is what we're looking for, minus 1 over T1, which is 587. And then you do the math to solve for T2, and you get an answer of 624 Kelvin. If you have trouble doing this math, please contact me and I would love to help you. Also, you will need to be able to use this same equation to solve for the activation energy or one of the rate constants. This is a reaction coordinate diagram. There are a number of things that you can find out from these diagrams. Here on the y-axis we have the energy, and it increases as you go up. At the very beginning you have the reactants, and they have a certain amount of energy, and then as they collide with one another with more and more force, they eventually get enough activation energy to react, and as the reaction is happening they form this activated complex, and that is a stage where the bonds of the reactants are elongating and the bonds in the products are forming. Once this activated complex is formed, then the energy is going to decrease until we have the energy here of the products. So there's a number of things you can find out from this diagram. First of all, if you were to calculate the change in energy, delta E, which is going to be E2 minus E1, so the energy of the products minus the energy of the reactants. In this case, the delta E is going to be negative. If the delta E is negative, the change in energy is negative, the reaction is going to be exothermic, which means it's giving off energy. In this case, the energy of the reactants is greater than the energy of the products. There are a couple other things that we can consider. What if we add a catalyst? Catalyst is a substance that provides a pathway with a lower activation energy in order to increase the reaction rate. So if you were to add a catalyst, this curve might look something like this. The reaction would happen faster. It's important to note that the delta E does not change, but the activation energy does change. We can also look at what would happen if we ran the reverse reaction. The reverse reaction in this case would have products with a lower amount of energy than the reactants, so the reverse reaction would be endothermic. In this case, we have products with a higher energy than the reactants, so the energy of the reactants is lower than the energy of the products. The energy of the reactants is here and the products is here. So if we took E2 minus E1, we would get a positive number. So this reaction is going to be endothermic. In an endothermic reaction, the activation energy is larger than in an exothermic reaction. In this case, if we were to add a catalyst, the curve might look something like this. And again, the activation energy does change when you add a catalyst, but the delta E, the change in energy from reactants to products, does not change. So an example like this gives us some numbers on our graph, and we can use them to calculate things. So first, it's asking if the reaction is exothermic or endothermic. A way that we can do that is to calculate the delta E, and the delta E is going to be E2 minus E1, or basically this is the energy of the products and this is the energy of the reactants. If we call this 0 and this 226, the E2 is the products, they have an energy of 0, minus the E1, the reactants, so we end up with a delta E of negative 226. So that's what we would put in here. And anytime delta E is negative, the reaction is going to be exothermic. And then you will look on the graph to find the number for the activation energy. In that case, that is this right here. So 132 kilojoules is the activation energy. And then on this problem, it's asking us the same thing, only we have a little different shape on our curve. So here are reactants. So that would be the E1. E2 is going to be here. So we could say that E2 392 minus 0 is 392 kilojoules. So here we would put positive 392. Because delta E is positive, it's going to be endothermic, meaning it has taken in energy. And then on an endothermic reaction, our delta E, our activation energy, is going to be much larger. So we have a 411 kilojoule activation energy in this case.